Good morning, everybody. Today we are going to discuss single phase full bridge inverter with R load. In the previous class, we have already completed half bridge inverter with R load 2 configurations and RL load 1 configuration we have already completed. Now this is single phase full bridge inverter having 4 switches here if you observe. So if you observe, this is one half bridge and this is one another half bridge. So therefore we can say that it is a two half bridges connected to a DC voltage sources. So otherwise we can call it as a single phase full bridge inverter. Right. In this, totally we are using 4 switches. So here what is the switching pattern? Here if you observe, the S1, S2 are one pair of switches and S3, S4 are one pair of switches. How can we give the triggering pulses means at a time we can give the triggering pulses to S1, S2 or S3, S4, but not this S1, S4 or this S3 and S2. What happens if we give the triggering pulses to this S1 and S4? Now let us assume if we give the triggering pulses to S1 and S4, these two switches will be turned on. Therefore, how the current flows? The current flows this plus Vs, switch S1 and S4 and to the return path. Now the total current flowing in this path means what happens? So the switches will be turned on, the entire current will be flowing like this means these two will be acting as a short circuit, right? So the source will be acting as a short circuit because of these two switches are turned on. Therefore, no current will flow through this resistive load. Entire current will flow through only these two switches. In a similar manner, if we give the triggering pulses to S3 and S2, the entire current will flow through this plus Vs, S3, S2 and to the return path. Again, it is acting as a short circuit. So because of if you give the triggering pulses either S1 and S4, S3 and S2 due to short circuit problem, so the devices may goes to damage, and one more disadvantage is no current will flow through the load. So because of this problem, so always we are giving the triggering pulse to S1 and S2 as well as S3 and S4, but not S1 and S4 as well as S3 and S2. Now we will go for the modes of operation of single phase full bridge inverter. So this is a single phase full bridge inverter. Now see, this is your V0 reference polarities. This is I0 reference polarities, right? So and so this assume this direction you can assume this source current reference current direction, right? So now from the first mode of operation, what is the interval is 0 to T1. That means 0 to T1. So which switches are on here? S1 and S2. When the S1 and S2 are turned on, therefore how the current flows is plus Vs, S1, R load, S2 and to the return path. Now, so because of giving triggering pulse to S1 as well as S2, these two are turned on, that is short circuit here. Okay. So now what happens here? The positive point will be connected to here and this negative point is connected here. Therefore, what is the output voltage? V0 is equal to Vs. So see here, V0 is equal to Vs from 0 to T1. Now, because of using resistive load, the shape of the current, what is the shape of the current for resistive load means whatever the shape of the voltage will existed here, the same shape will be presented here. Understand? So now coming to the direction, so this whatever the current is coming to the load like this blue color line, it is following your reference one. So that's why your current direction is also positive, or current direction is also positive, which is the shape which is same as that of your voltage because of resistive nature. For example, if it is a different load, the shape of the current waveform will be changes. We will look into the for RL load as well as RLC load later stages. Okay. So for from 0 to T1, the voltage is positive and the magnitude is Vs. And coming to the current, what is the magnitude is Vs by R. Now at T is equal to T1, I will switch off this gate pulses to S1 and S2, and immediately I will give the gate pulses to S3 and S4. So for that interval, what is that interval is T1 to T2. That means from T1 to T2, I'm giving the triggering pulses to S3 and S4, and S1 and S2 are turned off. Now see the next mode of operation from T1 to T2. From T1 to T2, S1 and S2 are turned off and S3, S4 are turned off. That means these two switches are turned on. Therefore, how the current will flows? Plus Vs, this S3 and R load S4 and to the return path. Now again, once we'll give the triggering pulses to this S3 and S4, what happens? This is short circuited and this device is also acting as short circuited, right? So now what happens? This point is appeared across here. See this one, this point is directly appeared across here. So and again, next, this negative point is appeared across here. Now look at here, this output voltage polarities are exactly opposite to that of your reference voltage polarities, right? So therefore, because of opposite, the output voltage is negative, which is very important, right? Next, what about the current direction? See, this current direction, blue color dotted line, this current direction is exactly opposite to your reference current direction. Therefore, what is the current is? Minus I naught. So that's why you are having negative, right? So this is the case. Now we have to find out the voltage across the devices to compare the half bridge inverter, right? Now, if you observe here, these two are in on state. That means this is shorted, this is shorted. That means on state. This is in on state, this is in on state, right? So, but what about S1 and S2 are off state? That means definitely a voltage will be existed across this S1 as well as S2. Now we have to write down the KVL equation, simple KVL equation. So minus Vs plus Vs1, next V0 and this Vs2 and to the return path, right? Of course, when S3, S4 are conducting, right, what is the output voltage is? Minus Vs. See, from T1 to T2. So when S3, S4 are conducting, what is the output voltage? Minus Vs. So if you substitute this minus Vs here, therefore what is the voltage across Vs1 is? Vs, Vs2 is equal to Vs. Understand what I am saying? Right. So now we have to compare this with your half bridge inverter. So in half bridge inverter, let us go for a half bridge inverter, one mode of operation for with the resistive load. If you observe this here, already we have done KVL equation. What is the voltage across Vs1 is equal to Vs. But what is the voltage across this load is Vs by 2 only. So while you are designing inverter, the output voltage is less, but your voltage across the switch will be higher. This is the disadvantage of in half bridge inverter. And coming to now, if you go for this full bridge inverter for R load, what we are seeing here, the output voltage is equal to Vs and the switch voltage is also equal to Vs. There is no ambiguity when you are designing this inverter. So this is the important point we have to consider, and this is the advantage we can say. So what we are saying, Vs1 is equal to Vs, Vs2 is equal to Vs, that is very advantage compared to half bridge inverter. In half bridge inverter, output voltage is Vs by 2, but the switch voltage is Vs. So whereas in case of full bridge inverter, V0 is equal to Vs, but V0 is equal to Vs as well as your Vs1 is also Vs. That is the advantage we have to say compared to your half bridge inverter. This is about your single phase full bridge inverter with R load. Right. Next we will go for RL load. So this is a single phase full bridge inverter with RL load. So here, if you observe carefully, for R load, this D1, D3, D4, D2 are off state in the second mode of operation. In the first mode of operation also D1, D3, D4, D2 are in off state. That means for resistive load, there is no requirement of this feedback diodes. But definitely for inductive loads, these feedback diodes are very important to send the power from load to source. Right. Now let us say, so during positive half cycle, not positive half cycle, I'm sorry, during T1 to T2. So that means this one, T1 to T2. See, I am not considering 0 to T1, this one. So while we are discussing here, it will be covered, the same it will be repeating here. So that's why I'm starting from T1 to T2. So from T1 to T2, when S1 and S2 are on. So when these two devices are on state, therefore, whatever the current will flows, plus Vs, the switch S1 and RL load S2 and to the return path. And here the inductor is present. So many times we have discussed what is the property of inductor. It will store some amount of energy and it does not allow sudden changes in current. That is the most important. Now whenever the current flowing like this, right? So this is following your reference current one. This is following your reference current one. So this is following your reference current one. Therefore, the output current is positive. That's why the output current is positive. Whenever the current flowing like this, right, and because of these two switches are on, this positive is appeared across here, this negative is appeared across here. Understand? Therefore, what happens? Whatever the polarities are there here, output voltage, those polarities are same as that of your reference voltage polarities. Therefore, this output voltage is positive. The output voltage is positive. That is the most important thing. Coming to the source current. What about the source current? See, this current direction is following your reference one. And therefore, the source current is also positive. Here, the source current is also positive. Right. And in this mode of operation, the inductor gets energized. And finally, I have written clearly here, this IS is positive, it is positive, V0 is positive because these polarities are following reference one, that's why it is positive. And I0, this, what are the current flowing here? This is I0. This is following your reference one, that's why your I0 is also positive. This is the first mode of operation. In the second mode of operation, what happens? See here, and second mode of operation means from T2 to T3. And immediately I will remove the pulses to S1 and S2 and I will give the triggering pulses to S3 and S4. But it won't turn on. The reason I will discuss carefully. Right. So now from T2 to T3, I will give the triggering pulse to S3 and S4. Right, but it won't turn on. But what happens? The feedback drivers will be conducted. What is the reason? So now, so if you give the triggering pulses to S3 and S4, the current should flow in this direction. The current should flow in this arrow mark direction, just this direction, towards from this path. That means exactly opposite to this red color line. So the current should flow in this fashion. But inductor does not allow sudden changes in current. So because of that reason, immediately the inductor polarity is reverses here. Inductor polarity is reverses. See, if you observe carefully, earlier this is plus and minus. Now what happens here? This minus and plus. Now because of inductor polarity is reverse, the current will flow through like this. So because see, this positive is applied to anode. Once this positive is applied to anode means what happens here? Obviously cathode is present, so therefore it is a forward bias. Similarly, whatever the negative is there, this negative is applied to this cathode. Therefore, here cathode negative means anode it is a positive. Therefore, it is also forward bias. So that's why the current will travels from this plus VL resistance, this diode, and to the source, and again to this D4, again to the return path. Right. So because of that reason, that means the current is flowing in this direction. See, the current is flowing in the opposite direction to this switch. See, this switch direction is top to bottom direction, and here this bottom to top direction, right? So opposite direction. So that's why even if you give the triggering pulses to S3 and S4, it won't turn on. So that is the important point we have to identify because of this inductor. So now the current is flowing in this fashion. So now see, so many times I told you, once the inductor polarity is reverses, whatever the polarities are there, the same polarities will be presented for the output voltage. See here, this is negative is there, you can get negative output voltage. This is positive, and you will get the positive output voltage. Understand? So that means here negative output voltage is negative. That's why from T1 to T2 to T3, the output voltage is negative. But what about the current? See, this current direction is following your reference current direction. So that's why still the current is positive. But the slope is negative because the inductor is discharging. In the first mode of operation from T1 to T2, inductor gets energized. Here what happens? The inductor gets discharged. That's why the slope is negative. So I'm coming to the source current. What about the source current? See, this is the reference direction. Now actual current is flowing in this direction. Both are in opposite direction. So both are in opposite direction means the source current is negative. So from T2 to T3, the source current is negative. So that is very important point we have to identify here. Right? So again, I have written here clearly, this IS is negative. So this IS means this one. This is negative, and V0 is negative. See the polarities. These polarities are opposite to that of reference voltage polarities, and I0 is positive. So that is the concept over here. Understand what I am saying? So, and at the end of this mode, what happens? The current reaches to 0. Now, whatever you have already given the pulses to S3 and S4, Now it will be turned on. Now S3 and S4 will just turned on. Right now we'll see that one. Right. So now because of current is reaches to 0, no reverse current flows through these switches S3 and S4. So now whatever the switches, whatever the pulses we have given to S3 and S4, now it will be turned on. Once it is turned on, how the current will flows? This plus Vs, this S3, RL load, and S4, and to the return. Understand what I'm saying? Now these two switches S2 and S3, S1 and S2 are off state. So the current will be flowing in this fashion. Right. Now we'll see. So first of all, the source current and the source current reference direction and source current actual directions now both are same. That's why IS is positive from T3 to T4. So from T3 to T4, the IS is positive. What about the current? See, this is the actual current direction, but your reference current direction is this one. Both are opposite directions. Now, see, this one is exactly opposite to your what happens I not reference. So the current is negative. See, this current is negative. Now the inductor will be energizing in this direction. The inductor will be energizing in this direction. Understand? And what about the output voltage? So because of current is flowing in this directions, because of switch S3 and S4 are turned on, see, this positive is connected to here, right? And this negative is connected to here, right? So because these two switches are on, this positive is directly appeared here, this negative is directly appeared here. Therefore, these two polarities are exactly opposite to that reference polarities. Therefore, output voltage is negative. So from T3 to T4, output voltage is negative. Right. Next, in the last mode of operation, right? In this mode of operation from T4 to T5, again we will give the triggering pulses to S1 and S2, but it won't turn on immediately. We will see that. So if you give the triggering pulses to S1 and S2, it won't turn on because of the inductor, right? So already the current is flowing in this direction. So up to here, this point, but inductor will not allow sudden changes in current, right? Direction. So the current will flow through this D1 and D2 because this positive is appeared to here D1 anode. Therefore, obviously here cathode. That's why it is forward bias. Next, this negative, right, or this negative, whatever both are same. This negative is appeared to D2 cathode. D2 cathode negative means obviously D2 anode is positive. Therefore, that's why this is forward bias. Now, so inductor will discharge its energy to this D1, this source, again D2, and to the return path. Right. Now, if you observe, this current is exactly opposite to this switch current direction. So that's why even if you give the triggering pulses at T4, it won't turn on. Right. So the current is flowing in this direction, reverse direction. So it won't accept. That's why this S1 and S2 are still it is in off state. Right. But the feedback diodes will be conducting in this direction. Right. Now, whatever the inductor polarities are there, the same polarities will be appeared across the output voltage or load. So now see, these two polarities are exactly opposite to that of same as that. No, I'm sorry. These two polarities are same as that of your reference polarities. That's why from T4 to T5 output voltage is positive. But what about the current direction? See again, this current is exactly opposite to that of your reference one. That's why, that is the reason the current still it is in negative. The current still it is in negative nature. Okay. What about the source current? See, these two are again opposite directions. That's why the source current is also negative. So whatever this D1, D2 is there, the same D1, D2 is presented, the cycle will repeat. Okay. So this is about your single phase full bridge inverter with RL load, right? So now coming to next one, single phase full bridge inverter with RLC load, lagging power factor. Lagging power factor means what happens? This inductance effect is more than that of your capacitive effect. That is a very important point we have to identify here. Therefore, the circuit operation so is similar to that of your RL load, no change. Whatever the first mode of operation here, the same first mode of operation will be presented. Everything will remain same. Everything will remain same. But what is the difference? Means this shape of the current waveform, and here also the shape of the current waveform. See, Earlier, what is the shape of the current waveform is triangular, because here we are using only RL and high inductive load. That's why the shape of the current waveform is triangular. Now here what happens, RLC load, then what is the power factor is lagging power factor. So because of lagging power factor, so the circuit will operate similar to your RL load only. But why this current waveform is changing into the sinusoidal? That is most important. So this one already have discussed in the class A commutation. So please refer the class A commutation in the first unit. Refer my notes. There you will get the current equation. What is that current equation is? Vs into root C by L into sine omega t. So that means the current is waveform is, depends upon the shape is sine. So that's why we are getting the sine waveform shape. Understand? The modes of operation is remains same only. So whatever the triggering sequence, see here S1, S2, D3, D4. Here also S1, S2, D3, D4. Next S3, S4, D1, D2. Here also S3, S4, D1, D2. What is this file? It's a power factor angle. So it's a cosine of angle bit difference between this voltage and current. See, voltage is started here, 0 reached here, and the current 0 is reached here. So some phase shift is there. That phase shift we can consider this one. This is the phi, cosine angle difference between voltage and current. So if you want, I can explain one or two modes of operation. So again the same from T1 to T2. When S1 and S2 are turned on, the current will flows plus Vs, this S1, RLC load, and S2, and to the return path. Now see, because of these two turned on, the positive point will be appeared here, negative point will be appeared here. Understand? Therefore, again, this is following your reference current voltage. So that's why voltage from T1 to T2 are positive. So and again, current is following the same reference one. That's why the current is also positive. Right. So, but because the shape is changed, just refer the RLC, classic commutation. So like that. And the second mode of operation, what happens is the polarity of the inductor is changed. Right. Therefore, D3, D4 will conduct. Again, the current will flows this inductor, RC, D3, and again voltage source and D4 and to the return. Same. Whatever I have discussed in the RL load, the same modes of operation, no change, but only the change is this current waveform. So that I already discussed in the classroom itself. Right. So now coming to the this RMS output voltage equations and harmonic analysis, which is similar to that of your half bridge inverter. But what is the difference? We will see here. So this is the formula for RMS output voltage equation. Not RMS, the average, if you take in the average sense, but we are taking in RMS case. So VRMS is equal to 1 by T integral 0 to T Vs into dt. So here what happens is we are considering only half cycle. We are considering only half cycle. For half cycle, what happens? 1 by T by 2 into 0 to T by 2 into Vs dt. If you take under square root, again this Vs square and both are gets cancelled. So for simplifying, I didn't use this under square root. Please remember this point, right? And what is the finally, if you get VRMS is equal to Vs, right? So here this T by 2, why I am taking T by 2? See, this is a symmetrical waveform. For a symmetrical waveform, always we have to consider half cycle. So that's why I have used T by 2. That is from 0 to T by 2. I didn't use square root. If you want, you can use square root and you will get the same thing. Because if you square it and this square and root gets cancelled, and VRMS is equal to Vs. What is IRMS is equal to VRMS by R? So what is IRMS is equal to VRMS is how much? Vs. That you can substitute here and you will get R. Or Vs by J. What is P is equal to VRMS into IRMS? So what is VRMS is nothing but Vs. What is IRMS is nothing but Vs by R. If you substitute, finally you will get Vs square by R. And Z is equal to square root of R square plus XL square, and Z is equal to square root of R square plus XL minus XC whole square. And coming to the harmonic analysis of full bridge inverter. So here we have to consider one full cycle, right? While you are doing harmonic analysis, we have to consider the full cycle rather than half cycle. Otherwise, if you are doing with half cycle, means you have to multiply it with some factor. So then you will get the answer. No problem for that answer, right? So therefore, I am considering here full cycle. So you already know the equation. So V naught is equal to A naught plus sigma n is equal to 1, 2, 3 and so on infinity. An cos n omega t plus Bn sin n omega t. And what is A naught? A naught is equal to 1 by t integral 0 to V of t d omega t. Substitute the time period t is equal to 2 pi, and from 0 to pi, what is this one? Vs d omega t plus from pi to 2 pi what happens? Minus Vs. See, this is minus Vs d omega t. Therefore, A naught is equal to 0. In the similar fashion for An, if you substitute, right, and finally An is equal to 0. But Bn, what happens is you will get some value. So what is that value? Is 2 Vs by n pi into 1 minus cos n pi. If you substitute n is equal to 1, let us say cos pi is minus 1, minus of minus plus, therefore 2 into 2, 4 Vs, that is 4 Vs by n pi. For example, if you substitute 0, that means even number. So cos 0 is 1, 1 minus 1, 0. That means for even values, Bn is 0. For odd values, Bn is 4 Vs by n pi. So this derivation already we have discussed in half bridge inverter. The only magnitudes are same. For half bridge inverter, he has Vs by 2. For full bridge, it is Vs. That's it. And this is the equation. And if you substitute the Bn value, because An and A naught are already 0, Bn value is 4 Vs by n pi sin n omega t. And therefore, finally, what you will get? V naught is equal to 4 Vs by n pi sin n omega t. This is nothing but Vm, because this is in the form of V naught is equal to Vm sin omega t. So that's why this is I can consider as a Vm. For I substitute n is equal to 1, then it is called as fundamental component. Therefore, V01 RMS is equal to Vm by root 2. So what is Vm is 4 Vs by n is equal to 1 divided by pi divided by again root 2. Then finally you will get 4 Vs by root 2 pi. If n is equal to 3, that is called as third harmonic. So Vm by root 2. What is n here? 3. So see here, I'm sorry. This is n is equal to 3. That means simply wherever n is there you have to substitute 3. And finally V03 is equal to 4 Vs by 3 into root 2 into 5. What is the harmonic factor? V0n divided by V01. So what is V03? 4 Vs divided by 3 into root 2 into 5 divided by V01. What is V01 is 4 Vs by root 2 into 5. And finally you will get 1 by 3, 33.33%. Similarly, for fifth harmonic, again you will substitute the equations. N is equal to 5 only, remaining everything is same. You will get 1 by 5 and so on. See, this 1 by 5, 1 by 7, this 1 by 3 are same as that of your half bridge inverter. Why? What is the reason? Means whatever the shape we obtained in half bridge inverter, the same shape also it is presented here also. So there also the output voltage is square waveform. Here also the output voltage is square waveform. So that's why what you are getting, this all values are same, but magnitude V01 magnitude is different. There you will get 2 Vs by root 2 pi. Here 4 Vs by root 2 pi. That is only the difference. And finally the THD is also same because of square wave, 48.3%. But here VRMS is Vs square. Earlier that is Vs square by 4. And again this is also changed. This V01 is also changed. 4 Vs by root 2 pi. To simplify, you will get this. Right? And in the last class I already discussed, as the harmonic factor is reduces means if the n value will be increases. The lower order harmonics have higher magnitude compared to higher order harmonics. This is just summary of what I have discussed. Now this is very important. Power in single phase full bridge inverter divided by power in single phase half bridge inverter. What is the power in single phase full bridge inverter? Vs square by R. What is the half bridge inverter power is? Vs square by 4R. Please refer the slides of your half bridge inverter. There I have clearly discussed this one. Right. And finally, if you simplify, what is P full bridge inverter is equal to 4 times of P half bridge inverter. This is very important. Why we are moving to half bridge to full bridge means this is the main reason. So we can obtain the power in single phase full bridge inverter is equal to 4 times of P single phase half bridge inverter. That is the most important thing. Understand? And coming to one more important point, the voltage across the half bridge inverter, the voltage across the switch for half bridge inverter is Vs. the voltage across the switches for full bridge inverter is also Ds. So that is also one advantage compared to half bridge inverter. So that is the reason we are going for only single phase full bridge inverter. One more disadvantage if you identify in half bridge inverter. So for anything you can take, right? So one circuit we will see. So in half bridge inverter for this one. So let us say this is half bridge inverter. In half bridge inverter, this is called as DC 3-wire system, right? So this positive and this negative is connected here, and the load is connected here. So that's why this is called as DC 3-wire system. A DC 3-wire system is also required in single phase half bridge inverter. So that is the reason generally nobody will go for half bridge inverter. So everybody will goes for full bridge inverter. So that is the main advantage of full bridge inverter rather than the half bridge inverters, right? Now if you see the simulation of single phase full bridge inverter, here I am using RL load, R load or RLC load. Right. So firstly, let us go for one simulation circuit. This is single phase full bridge inverter. So this is important. Right. So now here the load is, if you see the load, I'm showing here. So when you want to observe any waveform in single phase full bridge inverter, please take this RLC load, but not RLC branch. Right? My sincere advice. Right. So here, what is the input voltage I have taken? 100 volts I have taken. So first we will go for R load. R load means what happens? Active power. There is no reactive power. So I am making here 0, and this is also 0. I am making. Okay, and apply. And if you run the simulation, so if you run the simulation, so this is. So see, this is a simulation. Yeah. So now see, this yellow color indicates the voltage measurement, blue color indicates current measurement, right? So now whatever the shape is there, voltage waveform, the same shape here it will be obtained because of resistive nature. Understand what I mean? For resistive nature, both shapes are same, right? Next, coming to didn't see means see here. This whatever the voltage shape is there here, the same shape it is obtained. So voltage and currents both are in same phase we can say. So this is voltage measurement and this is the current measurement. Both are same. So this is your voltage, yellow color indicates voltage measurement, is the current measurement. So that is the thing. And next one, again if you want to go back here. So this is again if you change here, this is some 1000 VR I have connected and capacitance I didn't connect. That means we can consider RL load. So now if you observe the waveform, so this is the waveform. So for RL load, high inductive load, I said that what is the shape of the waveform is triangular. So but your output voltage waveform is remains same for any load because we are using voltage source inverter. What is meant by voltage source inverter? The output voltage is independent of the load and output current is dependent on the load. So that is the reason you are getting this voltage as this voltage. This voltage is square wave for any load, but current shape is changes. Right. So next we will go back to one more load, which is now this is nothing but here. This is 800. I will kept here. So RLC load. Now we'll observe the shape of the waveform. Now see what is the shape of the wave. So sine wave. You are getting a sine wave, but not it is a triangular wave or square wave. It is a sine wave, but RLC load. So now for what happens, this is leading power factor or lagging power factor that we can see here. See here the voltage is 0 here, but the current is 0 here. This is nothing but lagging power factor angle, right? So next one, let us say, if you go for the load, see here, why it is lagging power factor means your inductive power, reactive power is greater than capacitive reactive power. So that's why you are getting lagging reactive power. For example, if I change it, then to run the simulation, now I'll get leading power factor. Now see. So this is your leading power factor. Now if you observe carefully, yeah. So now see, first the current reaches to 0 here, next the voltage is reaching 0 here, right? So this is nothing but leading power factor angle, right? Because the capacitive reactance, capacitive reactive power have used higher reactive power have used. So here, see if you want here 1200 and this is 100. So this is the reason why we are getting leading power factor angle as well as the lagging power factor angle, right? Next, if you come back again here, and I have done the harmonic analysis for resistive load. So for resistive load, again, if you observe the voltage waveform, one cycle, what is THD? 48.33. Already we have derived here. I think, yeah, this is 48.3. And coming to what is this? Third harmonic 33, fifth harmonic is 20, seventh harmonic is 14.2. Same as that of your half bridge. But what is the difference is this value. This value is very important. Why? Because here just now I have shown in the simulation, I have used this VSC is 100. Substitute here V01 is equal to 4 into 100 divided by root 2 into pi. Then definitely you will obtain this 90.01 RMS. If you multiply with root 2 for the resultant, you will get this one, right? So this is important point you have to understand. Now here we will go for one important observation. So what is that important observation? Right. So for resistive load, for the feedback diodes, feedback diodes are not used for the mode 1 operation and mode 2 operation. For the inductive load, the feedback diodes are using here, right? Let us say if these feedback diodes are absent, for RL load, what will happen? That is the most important point we have to identify, right? Further, if I want to use one half bridge inverter, so which already have discussed. See, look at here, carefully understand. For the positive voltage output waveform, I have used a switch with anti-parallel diode. For negative half cycle output waveform, I am using a switch, but it is not a diode. Understand what I am saying? So while you are doing the experiment, for the positive half cycle, you don't have any problem. That means because you are using a feedback diode. For a negative half cycle, we are not using a feedback diode. Because we are not using any feedback diode, a high voltage spikes will occur. Why the high voltage spikes will occur? Because you are not discharging your inductor energy. You are not discharging your inductor energy to the source, right? So due to this reason, a high voltage spikes will occur. Because if you are not discharging your inductor energy, then what happens? The current flowing through this switch is going to be 0, right? So suddenly the current you are making from some maximum value to 0. That means inductor is allowing what happens? Sudden changes in current, therefore which leads to a high voltage spike. Understand what I am saying, right? Now we'll see, already have discussed this half bridge inverter. That means in the first mode of operation, when this switch is on, how the current will flows? The current will flows this capacitor and through this load, right? One more current is this voltage source, this switch, and this RL load, this capacitor, and this, right? This mode of operation I have already discussed. That means in the first mode of operation, this inductor gets energized. In the second mode of operation, what happens? We will remove the pulse to this one. Then this polarity of the inductor will changes. Then D2 should conduct. That means here anti-parallel diode should conduct actually, right? So the current should flows in this fashion one, and one more current is the current should flows in this one, right? You please refer the slides for mode 1 and mode 2 operation for half bridge inverter for this configuration, right? So now because of using this feedback diode here for positive half cycle waveforms, you won't get any high voltage spike. Here what happens, because of you are not using any high voltage, you are not using any feedback diodes, you will get the high voltage spike. The high voltage spikes, why it is coming means you are not able to provide the discharge path for this inductor energy. So for that, what happens is this current will goes to the switch cannot allow the current in the reverse direction. So that's why what happens is the current will goes to zero immediately, and because of inductor is allowing the current is zero, so a high voltage spikes will obtain. So now that I will show in the simulation clearly. So once I am running the simulation, first of all, for run the simulation, and I will get this one. Yeah. Now, if you observe carefully, so these are the high voltage spike. First of all, where is the output? So why the output is not clear means see here, this spike magnitude is minus 16 into 10 power 4. Minus 16 into 10 power 4. That is most important. Why I'm getting spikes in the negative half cycle only? I said clearly, the feedback diode I have used in positive half cycle case. That means upper switch, and I didn't use any feedback diode for the negative half cycle switch, right? That means lower side. So that's why for the negative half cycles only I'm getting the spikes. Now I will show the output waveform where it is clearly. So see this. This is your output voltage. This is your output voltage. We are getting output voltage. For positive half cycle, you are not getting any high voltage spike, but negative half cycle, I am getting high voltage spike. But if you having the current waveform, right? So this waveform you can see. So both voltage and currents are available here. Now, if you observe, so for this, so see, yeah. So now, if you observe carefully, understand, please. So now see here, this current is discharging perfectly, no problem. This current is discharging perfectly. But if you observe here at this moment, right, I will zoom it. So now if you zoom it this, and also, yeah. Now see here at this moment, at exactly, see 0.03 time, the current is suddenly zero. The current is going, suddenly it is going to be zero. So now at 0.03, a high voltage spike is obtained because you are not providing any discharge path. See in the simulation diagram, if you want, you can observe. See here you are not connected any feedback diode. The current should not goes through this switch. So because the switch current direction in this one, so here the current will not flows in this direction. Therefore, the current is zero. Because of current is zero, the circuit is acting as an open circuit. A high voltage will be obtained here. So that is because of inductor. So because you know that V is equal to L into di by dt. So within a short time, if change in current, that is di, if it is zero, then what happens here means a high voltage spikes. A high voltage spike. This spikes will be obtained. This spikes. So that I have shown clearly, this high voltage spikes is coming, and why this high voltage spikes is coming means this current at this moment, the current is reached to zero. So reach to zero. Suddenly it is reaching to zero. See, the current is changing from 2 amps to zero within a very short time. So that's why high voltage spike will be presented. So this is the problem will be presented when you don't use any feedback diode. So while you are connecting RL load, definitely a feedback diodes will be required, right? So in this class, I have discussed So RLC lagging power factor load, but leading power factor load operation will be different. That I will discuss next class. For the next class, these operations are very important to understand. Next class we will continue. Thank you.